Let me just exemplify how we can use the maximum likelihood principle within a specific distribution, namely the binomial distribution. What would the principle of maximum likelihood lead to? Basically, I will show you that it leads to common sense, to basically do what most people would do. But it's nice to see that the general principle of maximum likelihood that I introduced in another small video does actually make sense in any context, actually. For instance, the binomial. So let us assume that we have something which is binomially distributed like this, NP. We could also see it differently. When we have something which is binomial with n, we could see it as having n individual coin throws. So we have n of those that are independently, all of them binomially distributed with n equal 1 and the same p. So that would be a different way of looking at it. So usually in probability theory, these are called Bernoulli variables. When the binomial n is 1, it's called a Bernoulli variable. It's still a binomial, a specific kind of binomial. Then to apply the likelihood principle, to write out the likelihood function. Well, basically, the theta here would be p. P is the unknown here in this model. So we want to infer about p. We want to find, for instance, the maximum likelihood estimator of p. So we should see it as a function of p, and then in a way as a function of observed data, if we assume that we have an observed sequence of these n Bernoulli variables. That is then the joint density of these ones. They are independent, so it's the product from 1 to n of each individual binomial with n equal 1. So it would be, the binomial, that would be p to xi, and then 1 minus p to 1 minus xi. That is the probability of seeing exactly x1 in the first one, x2 in the second one, x3 in the third one. So I basically take the probabilities from the binomial density function or the binomial probability function, plug into this likelihood, and here is the likelihood function. As I said in the general presentation, I would usually consider the log likelihood when I'm going to actually do my maximization. The log likelihood as a function of p, suppressing the dependence of x in the notation again, is then the sum of y up to n. Then I take the log, that is xi log p, plus 1 minus xi log 1 minus p. I'm using rules for logarithm calculations here. This is the log likelihood function. Now, if I am going to find the maximum likelihood estimator of p, I should maximize this function with respect to p. How do I maximize a function? I find the derivative. I find the derivative with respect to p. I look at the likelihood function, and then I start finding the derivative. I take the first part here. I take the sum inside also now. So in a way, I could take the sum inside first if I wanted. Then I could say the first term here basically is the sum of xi times log p, and the second term is the sum of 1 minus xi times log 1 minus p. That is sort of simplifying the log likelihood function a little bit. Now I do the derivative of this. Now the log p, the derivative of log p, that's 1 over p. And then I have the constant. Because seen as a function of p, the data is just constants. It's just something plugged into the function. So it's kind of an easy thing. It's just the sum of the xi. What about the second term here? Then I have to take, again, it's the derivative of log 1 minus p. That is then, actually that becomes minus 1 over 1 minus p. Because log something is 1 over this, and then there's an inner function. I'm doing the derivatives a bit fast here, assuming that this is something we've learned. Hopefully I do it correctly. I'm just checking my numbers here. Looks okay. Then I'm still lacking the constant here. The constant, which is the sum of 1 minus xi. Then to maximize a function, you take the derivative and equal the derivative to 0. That's the classical optimization in mathematics. And you try to solve for p. Let's see if we can solve for p in this one. If we do a bit of calculation, we see that 1 minus p times the sum of xi, this is equal to p times the sum of, I say n minus the sum of xi. I've changed this one into n minus the sum of xi. And then we solve this for p, and we get p equal the sum of xi divided by n, which is then the well-known solution that if you in the binomial, you're going to estimate the underlying proportion p. Of course, what would you do? You would count the number of successes and divide by the total number n, and that gives you the estimate of p, right? So we could add that this is then the maximum likelihood estimator. So what we usually do in the binomial is actually maximum likelihood estimation of p. This is nice. So we could actually pursue the use of likelihood methods for doing confidence intervals and hypothesis testing in the binomial setting, which is a nice way of doing statistics for the binomial without using the approximative assumptions of the normal. But that's for another day in another lecture. So thank you on this one.